You have been lied to your entire life. Every time you plug your phone into a charger, every single day, you are operating on a completely false understanding of what is actually happening inside that cable. Most people picture electricity the way they were taught in school, as a stream of tiny particles racing through copper wire at nearly 300,000 kilometers per second, rushing from the wall outlet to your phone like a bolt of lightning trapped inside a metal tube. It sounds reasonable. It sounds logical. It is completely wrong. And here is the proof. If physical matter and electrical charge were genuinely traveling at that speed and slamming into your device, the energy transfer would destroy your phone in a fraction of a millisecond. It would ignite instantly in your hand, but it does not. Instead, it sits there quietly for 2 full hours, slowly climbing from 0 to 100%. That gap between what we imagine and what actually occurs reveals one of the deepest and most overlooked truths in all of physics. The real story begins with something called drift velocity, and it will permanently change how you understand the world around you. Inside a copper wire, atoms are packed tightly into a rigid crystalline structure. The electrons that everyone assumes are sprinting through that structure are not sprinting at all. They are crawling. Every time an electron attempts to move forward, it collides violently with a massive copper atom, bounces backward, loses energy, and collides again. The actual average forward progress of those electrons through the wire is approximately 1/4 of a millimeter per second. Read that again, 1 millimeter every 4 seconds. If you could paint a single electron red at the wall outlet, that specific electron would take hours, possibly days, to travel the length of a standard charging cable. The idea that electrons race to your phone at the speed of light is not a simplification. It is a complete fabrication. But this immediately creates a problem that should stop you cold. If the electrons move that slowly, slower than a garden snail, slower than almost anything you can observe with the naked eye, then why does your phone screen respond the instant you plug it in? How does your device know that power has arrived if the physical particles have not even left the outlet yet? This is not a trivial question. It sits at the boundary between particle physics and field theory, and the answer dismantles nearly everything you think you know about electricity. The key is understanding that what travels at close to the speed of light is not matter. It is a field. Think of a 1-kilometer plastic tube packed completely full of marbles from one end to the other. If you push a single marble into your end, a different marble falls out the opposite end almost instantly. The marble you touched barely moved a millimeter, but the pressure wave, the physical impulse, traveled through the entire chain at tremendous speed. Electricity works on precisely the same principle. When you connect your charger, an electromagnetic wave propagates outward through the space surrounding the cable, guided by the metal, traveling at an enormous fraction of the speed of light. That wave reaches the electrons already sitting inside your phone in essentially no time at all, delivering the command to move. The push is nearly instantaneous. The field is already there. So if that commanding force arrives at your device in the blink of an eye, why does filling your battery still take 2 hours? The answer lies in a battle happening at the atomic level, a battle that the laws of physics will not allow anyone to rush. To understand why your battery takes 2 hours to charge despite receiving its marching orders almost instantly, you first need to abandon another deeply ingrained misconception. Your battery is not an empty bucket waiting to be filled with a glowing liquid called electricity. That mental image, however intuitive it feels, is dangerously inaccurate. What happens inside a lithium battery is not a simple filling process. It is a controlled chemical conflict, and physics has no tolerance for impatience. A lithium-ion battery is, at its core, a precisely engineered chemical reactor divided into 2 distinct sides, separated by a physical barrier. When the battery is depleted, all the lithium ions, real, solid pieces of matter with mass and volume, are crammed on one side, completely discharged. When you plug in your charger and that electromagnetic wave strikes the interior of your device at near light speed, it is not depositing new particles. It is delivering a force and an unavoidable command. That command reaches the electrons and drives the lithium ions to tear away from their resting position, push through a thick chemical medium, and physically migrate to the opposite side of the battery, where they are stored under enormous tension. Here is the core of the mystery. The energy signal travels at close to 300,000 kilometers per second, but the lithium ions are complete atoms. They have mass, they have inertia, they have physical volume that must navigate a microscopic chemical environment. Imagine the electrical signal as a general broadcasting orders over radio. The command crosses the battlefield at the speed of light and reaches every soldier instantly. But the soldiers themselves, representing the lithium ions, must cross a dense and sticky swamp while carrying heavy packs. No matter how loudly the general broadcast, no matter how powerful the transmitter, the soldiers can only move through that mud at a maximum physical rate before collapsing from the effort. The bottleneck is not electricity. The bottleneck is matter itself, the stubborn, heavy, and compromising reality of atoms trying to force their way through microscopic physical space. Now consider what happens if you try to override this limitation by force. What if you designed a charger that hit the battery with such overwhelming voltage that it compelled all the lithium ions to cross that chemical swamp in a single second instead of 2 hours? The laws of thermodynamics do not accept that proposal. Pushing matter through chemical resistance too rapidly generates catastrophic friction at the atomic level, and that friction converts immediately into uncontrollable heat. If lithium ions were forced to absorb a full charge instantaneously, the liquid inside the battery would boil within fractions of a second. The chemical structure would collapse entirely, releasing highly flammable gases that would rupture the glass and metal casing and turn the device in your hand into a fragmentation device detonating at point-blank range. Your phone does not take 2 hours to charge because the technology is inadequate. It takes 2 hours because that is precisely the amount of time required to keep you alive. There is a small microprocessor inside your device acting as a strict gatekeeper. It senses the enormous electromagnetic energy arriving from the outlet and partially closes the door on it, allowing power to enter in carefully calculated increments, mathematically monitoring how much force the lithium ions can absorb at each moment without hitting past the threshold of catastrophic failure. The charging speed you experience is not a limitation of the electricity. It is a safety protocol written into the physics of matter itself. But this answer immediately generates a more troubling question, one that most people never think to ask. If the wall is pushing with massive, constant energy and your phone is deliberately blocking most of it, where exactly does all that waiting power go? Most people, when they consider this question, instinctively reach for the water pipe analogy. They imagine electricity as water, cables as hoses, and the phone's resistance as a partially closed valve at the end. Under that mental model, when the outlet pushes hard and the phone limits the intake, energy must be accumulating at the tip of the cable building up, pressing against the barrier, waiting in an increasingly compressed queue to force its way through. This picture feels logical. It is also a profound misunderstanding of how electromagnetic energy actually behaves, and correcting it requires grasping a concept that most people never encounter outside of advanced physics. What your wall outlet provides is not a fixed quantity of energy firing blindly forward. It is a potential, specifically a difference in electrical potential that physicists and engineers call voltage. Think of an enormous, dark ocean held behind a massive dam. That ocean contains an absolutely destructive amount of energy, the mathematical capacity to level entire cities if released all at once. But if you open a tiny tap at the base of the dam, you do not receive the crushing weight of the entire ocean bearing down on you simultaneously. You receive precisely the thin stream that fits through the tap opening. The ocean does not rage against your small valve. The water does not compress itself trying to smash through the metal. It simply remains there as potential energy, waiting for a pathway to open. Your phone is the controller of that tap. The internal microprocessor continuously adjusts electrical resistance, effectively widening or narrowing the opening based on what the battery chemistry can safely absorb at each moment. By doing so, it instructs the vast ocean of energy available in the electrical grid, I require only this precise fraction right now and nothing more. And the universe, following the rigid and unbreakable laws of physics, delivers exactly that fraction. Not one electron more. The energy that is not requested is simply not drawn from the grid. It remains as potential, not as a frustrated crowd pressing against a locked door. But the universe never delivers anything for free. Every energy conversion extracts a toll, and this particular toll is one you can physically detect right now without any instruments. The electricity arriving at your wall outlet oscillates, it reverses direction dozens of times per second in a rhythmic pattern called alternating current. Your battery, however, is a strict one-directional storage device that demands a steady, constant flow of current moving in a single direction. The charger block, that small plastic cube between your cable and the outlet, exists specifically to take the wildly oscillating energy from the wall and tame it into the calm, steady, low-voltage current that the battery will accept. The components inside that cube, the rectifiers and transformers, undergo enormous physical stress performing this conversion. Touch the charger block after your phone has been charging for an hour. It will be warm, sometimes uncomfortably so. That heat is not a manufacturing flaw or a sign of poor engineering. It is the physical manifestation of the second law of thermodynamics playing out in the palm of your hand. Every time energy changes form, some portion of it degrades into disordered heat that disperses into the surrounding environment. That warmth radiating from your charger represents electricity that never reached your battery energy, sacrificed to the universe's insistence that no conversion is ever perfectly efficient. Every charge cycle contributes a tiny, irreversible increase to the total entropy of the cosmos. And with that established, we arrive at the piece of this puzzle that will genuinely fracture your understanding of physical reality, because everything covered so far, as counterintuitive as it has been, is actually the easy part. Your entire life, you have looked at electrical cables and assumed the same thing without ever questioning it. The plastic on the outside insulates and protects. The metal on the inside is the pathway, the channel through which electrical energy flows from source to destination. After everything explored so far, the electrons inside that metal travel at roughly 1/4 of a millimeter per second, while the electromagnetic wave that activates your phone travels at a substantial fraction of the speed of light. Hold those two facts together simultaneously, and let the logical consequence surface on its own. If the electrons are essentially stationary, and the energy travels at near light speed, then the energy is clearly not riding inside the electrons. So where precisely is it traveling? The answer, supported by the fundamental and immutable equations of electromagnetism, is this. The energy charging your phone does not travel through the interior of the copper cable. It never has. It travels through the space outside the wire, through the insulating plastic, through the air immediately surrounding the cable as an electromagnetic field propagating along the outside surface of the conductor, not through its interior. The copper is not a pipe. It is a guide rail. This was not a fringe idea or a controversial hypothesis. It was formally demonstrated over a century ago by a physicist named John Henry Poynting, who proved through rigorous mathematics that the direction and density of electromagnetic energy flowing through space is determined entirely by the interaction between the electric field and the magnetic field at right angles to each other. This geometric relationship, now called the Poynting vector, shows that the actual power measured in watts flowing toward your battery travels through the insulating material and surrounding space, while the dense metal core in the center serves purely as a boundary condition, forcing the fields to maintain a specific shape rather than expand freely outward in all directions. Think of it as railroad tracks. The steel rails lying fixed in the ground do not carry the passengers. They do not contain the kinetic energy of the train. They are completely passive structures whose only function is to constrain and direct the machine that moves through the space above them. Your copper wire is performing the identical function for your electromagnetic energy. The energy moves through the space outside. The metal defines the corridor. If you could wear glasses that made electromagnetic fields visible, you would see a brilliant, intense stream of energy flowing through the air and plastic surrounding your cable, while the copper interior appeared comparatively dark and quiet. And here is the detail that makes this genuinely strange. When you hold your charging cable, the energy flowing toward your phone is passing through your fingers. It moves through the space occupied by your hand, guided by the fields constrained around the wire, without chemically interacting with your biology in any meaningful way. You are holding something that energy is flowing through and you cannot feel it at all. Once you accept that electrical energy travels outside the cable rather than through it, a natural question follows immediately. If the power is already moving through the air and the plastic, why not simply remove the cable entirely and let the electromagnetic field travel freely across the room directly to your phone? Why not eliminate the wire altogether and charge wirelessly from a distance? The answer to that question reveals one of the most mathematically brutal and unavoidable rules in all of physics, a principle so fundamental that no engineering innovation, no matter how advanced, will ever overcome it. It is called the inverse square law. Picture a light bulb switched on at the center of a large, completely dark room. Light radiates outward from that bulb in every direction simultaneously, expanding as a perfect sphere growing at the speed of light. But the total amount of light generated at the filament is fixed. As that invisible sphere grows larger, that same fixed quantity of energy must stretch to cover a three-dimensional surface area that increases with the square of the distance. Move twice as far from the bulb, and the light is not half as bright, it is 1/4 as bright. Move 3 times as far and it becomes 1/9 as bright. The energy density dilutes through space with terrifying mathematical speed. Apply this directly to wireless charging over meaningful distances. If you attempted to send the continuous power required to charge your phone from a wall-mounted emitter across even 1 meter of open air with nothing guiding the field, the meter would behave like a crude radio antenna broadcasting electromagnetic energy outward in every direction equally. By the time a tiny fraction of that expanding energy sphere reached the receiving antenna in your phone, the field density would have weakened by millions of times compared to its original intensity. To compensate and deliver even the modest 5 to 10 watts your battery chemistry requires, you would need to inject tens of thousands of watts into the emitter. The electromagnetic field generated would instantly destroy every piece of electronics in the building, vaporize moisture in the air, and represent a thermodynamic catastrophe of spectacular proportions. This is precisely why the humble copper cable, far from being a primitive or outdated technology, is actually one of the most elegant physical solutions ever implemented. The wire does not carry energy through its interior. It performs something far more sophisticated. It acts as a geometric cage for an electromagnetic phenomenon that would otherwise scatter uselessly into three-dimensional space. When you connect your charger, trillions of electrons distributed across the microscopic surface of the copper, moving individually at their characteristic crawl, respond instantaneously to the voltage applied across the circuit. They reorganize along the entire length of the metal surface, creating an absolute mathematical boundary in the surrounding space. This boundary, formed by slow-moving electrons acting collectively, takes the colossal electric and magnetic fields that would naturally radiate outward in all directions and compresses them ruthlessly. It forces those fields to maintain a cylindrical shape, clinging to the outside of the insulating plastic, propagating along the precise path that the copper geometry dictates, traveling at close to 300,000 kilometers per second straight to your device. The slowest particles in the system are simultaneously controlling the fastest energy in the universe. Every element of this system now stands clearly revealed, but one final boundary remains, and it is the most remarkable transition in the entire process. We have established that the energy arrives at your device as an electromagnetic field, invisible, massless, traveling through space at an immense fraction of light speed, contained and directed by the geometric boundary that slow electrons in copper create. But your battery cannot store fields. It cannot accumulate electromagnetic waves or absorb oscillating perturbations in the fabric of space. Your battery is a strictly material, strictly chemical device. It stores matter lithium ions held under tremendous electrochemical tension. So how does the immaterial become material? How does the ghost become physical? At the precise point where the energy field meets the intricate architecture of copper, gold, and silicon inside your phone's charging port, a transfer occurs that is simultaneously the most ordinary event in your daily life and one of the most profound physical transactions in nature. The electromagnetic field collides with the cloud of stationary electrons residing in the internal circuitry of your device. In that collision, the field does not bounce or reflect or pass through. It collapses. It surrenders its geometric existence entirely, transferring its energy instantaneously to those static electrons, forcing them to begin moving in a specific controlled direction. The energy ceases to be a spatial disturbance and becomes electromotive force, a physical pressure on particles. That pressure is what generates the actual electric current that flows into your battery. That current is what seizes the heavy, sluggish lithium ions and drags them through their thick chemical medium, one fractional millimeter at a time, accumulating tension in the battery chemistry with each microscopic displacement, generating heat that you feel radiating through the back of your device as the physical signature of entropy being produced in real time. The entire chain is now complete and visible in its full complexity. A potential difference at the wall generates an electromagnetic field. That field propagates at near light speed through the space outside your cable, constrained into a cylinder by the geometric boundary created by slowly drifting electrons in copper. It arrives at your phone essentially instantly, collapses into the device's internal circuitry, converts from field to force, drives a measured current through the battery chemistry at a rate precisely calibrated to prevent thermal runaway, moves lithium ions through their electrochemical medium at the maximum safe speed, and dissipates excess energy as heat throughout every component in the chain, the battery, the circuitry, the charger block, and the electromagnetic field itself. What looks like a mundane act plugging in your phone before you sleep is actually a sequence of events spanning quantum mechanics, classical electromagnetism, thermodynamics, and relativistic field theory, all occurring simultaneously in the object sitting on your nightstand. The cable is not a pipe. The electrons are not sprinting. The energy is not inside the metal. The battery is not a bucket. And the 2-hour wait is not an inconvenience. It is physics protecting you from a chemical reaction that, if uncontrolled, would be genuinely dangerous. Every assumption that felt obvious turns out to be a placeholder for a far stranger and more extraordinary reality. The universe operating around you at every moment is incomparably more sophisticated than the diagrams drawn on classroom whiteboards would ever suggest. If this completely changed how you think about the technology you use every day, share it with someone who still believes electrons sprint through copper at light speed and subscribe, because the gap between what we are told about reality and what physics actually reveals runs far deeper than a charging cable. There is much more to dismantle together.